A very good afternoon to everyone. The Department of ECE heartily welcomes the dignitaries, guests of honor, and the participants to the one-week FDP on impact of AI, robotics, VLSI, and medical domains from 22nd April to 27th April 2024. VVIT was established in the year 2007 by Sri Vasireddy Vidyasagar Garu and the Social Educational Trust. VVIT has self-contained infrastructure amidst the lush green paddy and maize fields of Nambur. VVIT is accredited with NBA and NAC A grade and is permanently affiliated to JNTU Kakinada. This institute has been conferred with autonomous status in the year 2019. VVIT offers 11 undergraduate programs and 5 postgraduate programs with a total intake of 1740 students every year. The main objective of the FDP is to clearly describe the importance of applying AI in various domains like robotics, VLSI, and also to discuss the recent trends. We here have a wonderful opportunity to learn from the experts of this field through this one-week FDP. I now invite Dr. Riyazuddin Garu, Coordinator FDP, to give a brief report on the FDP. So please.
Okay, madam. Thank you. Good afternoon. I cordially welcome all participants on behalf of Department of ECE VVIT to this one-week faculty development program on impact of AI, robotics, VLSI, and medical domains, which is starting from today to 27th April 2024. Actually, the main objective of this faculty development program is to equip faculty members with the necessary knowledge and resources to integrate AI-related concepts and technologies to their teaching curriculum effectively and utilize these acquired skill in the pursuit of their research. And the participant can gain some exposure from this session, which are handled by the experts from prestigious NITs and Central University. And this activity will not only enhance the knowledge and skills of faculty members, but also enable them to incorporate cutting edge advancements in AI into their teaching methodologies and research endeavors. For registration onwards, we are having 203 participants. Then 3 participants are registered for this FDP, representing nearly 60 colleges from across India, with a majority hailing from AP, Telangana, as well as the states like Kerala, Haryana, Pune, and I asked all the participants to attend all this within the time and join the sections, interact with persons effectively, and not only that, they can avail some sort of knowledge which will be useful for the students in their curriculum. And I request all the participants that after the session, we are going to share some FDP feedback daily. You have to give feedback, and as for that, into the future FDP are going to be conducted by our Department of ECE. Thank you. Thank you, madam. Thank you for giving this opportunity as a coordinator for this FDP. And I thank our department HOD, principal, dean of academics, and the management who are supporting us to conduct this type of FDP in our campus. Thank you, ma'am.
Thank you, sir, for briefing the session. I invite our head of the department, Dr. M.Y. Bhanumurthy Garu, to address the participants. Sir, please.
Thank you, Vinada madam. I hope I'm audible.
Yes, sir. Yes, sir. It is audible.
Okay. We are experiencing very hot summer this year. in the month of April itself. So I was wondering, should I say good afternoon to all? Rather, I would say namaste to everyone. Firstly, I would like to thank our Honorable Chairman, Sri IETE Vijayawada Garu, for his support and blessings. It is a norm for a department to conduct at least 2 FDPs in an academic year, 1 in each semester. So mostly one will be online, the other one will be offline. And this year we came up with the impact of AI. And thanks to the resource persons, we have a wonderful lineup of experts from various prestigious institutions, tier 1 institutes, more specifically. And also, I came to know that around 200 participants from various colleges across India have registered for this 1 week FDP. As a teacher, we are always a continuous learner. So we are all learned people who have registered for this program and also might have attended many other programs and will be attending programs in future too. So please be a continuous learner and also please make sure that you are taking away good aspects, knowledge from these FDP from the resource persons. So that you are publishing good research papers in future. Those who are scholars, it might be helpful, and also those are willing to pursue their PhD. These type of FDPs will always help in understanding what are the current research domains in varied fields. So I do hope that this particular FDP on impact of AI on various domains will help all the participants. And I also request all the participants to kindly tune into this FDP live daily from 2 to 4. And also please give your feedback daily so that every one of you can receive a participation certificate. And I also warmly thank the chairman of IETE, Dr. P. Rajshekhar, for his presence, despite having a NBA compliance meeting in his institution. So this particular FDP is being conducted in association with IETE Vijayawada Centre. So I also thank IETE Vijayawada Centre for their support and the funding that is given to IETE to this particular FDP. So please respond to the messages in the group or when we are sending it in person, either through email or through WhatsApp. And also, if we are doing any calls, please kindly respond to them. So that is how we can have mutual respect among each other. Okay. So once again, thank all the participants. Let us hope that this particular 1 week FDP will be productive and fruitful. Thank you.
Thank you, sir. Thank you for guiding us. I now request our Dean of Academics, Dr. K. Giribabu Garu, to speak a few words on this occasion. Sir, please.
Thank you, Vinil Garu. Okay, namaste and good afternoon, everybody. First of all, my congratulations and best wishes to ECE department for planning and organizing this 1 week online faculty development program on impact of AI, robotics, VLSI, and medical domains from 22nd April to 27th April. I welcome all the participants who registered and joined from various institutions working as a faculty and research scholars. I would also like to extend my sincere gratitude to all the expert resource persons for their kind consent to share their valuable knowledge. I wish this FDP would cater all the participants in satisfying the quest for exploring innovations in artificial intelligence and its impact with the trending technological advancements. On behalf of VVIT, I thank and honor the acceptance, readiness, and virtual presence of the distinguished resource persons across India who are going to share their invaluable knowledge acquired through their relentless hard work. I present a bow of respect to the chief patron for this FDP, our chairman, Sri Vasireddy Vidyasagar Garu, Principal Dr. Y. Mallikarjun Reddy Garu, who supports us always to take up any challenging step forward into the realization of our VVIT's vision. And I congratulate HOD Bhanumurthy Garu, Coordinator Riyazuddin Garu, Inaul Haq Garu for conducting this faculty development program. I once again convey my best wishes to all the wise participants of this FDP who are all set on this virtual platform, ready to imbibe every key point in this program. We wish this FDP will achieve its objectives in a fruitful manner. Thank you. Thank you, one and all.
Thank you, sir. Thank you for your encouraging words. I now request our beloved principal, Dr. Y. Mallikarjun Reddy Garu, to address the participants. Sir, please.
Good afternoon to all the participants. A one-week faculty development program on impact of AI, robotics, VLSI, and medical domain. This is starting from today and up to 27th April. It is organized by Department of Electronics and Communication Engineering and in association with the IETE. So welcome to all the participants. And first of all, I congratulate all the resource persons who accepted the deliver. It's a very for giving their consent, and also the participants who are participating from various engineering colleges to know about the emerging technologies like artificial intelligence, how it is related to the different domains is a very, very important. At present, it is the very demanding area where the AI-related concepts are applicable in many engineering applications like robotics, VLSI, wireless networks, and medical imaging, and so on. Right? So it is an interdisciplinary concept where all the teachers can learn about the technology and how this artificial intelligence and natural language processing NLP, it is going to impact on the social networks and social media, right? And various strategies, development technologies are going to learn in this workshop. So mainly in the semiconductor domain, as you know that when we are using very large scale integration, VLSI, right? And it is a emerging area in which the semiconductor devices, right? It is entering into nanotechnology, right? Where we can use the many types of processors in many applications, like in electronic vehicles, drones, right, robotics, and any applications. The semiconductor processes are very, very much needed, and they are going to give a lot of impact on the development of technology in the hardware side. And similarly, we have that integrating AI with wireless sensor networks that is related to the 6G technology. 6G is now entering, right, where this communication is how the AI techniques, right, such that we can make very high speed data networks and cloud computing can be used, right, in wirelessly, right? And deep learning, machine learning, or techniques, right, are have a lot of strategies are developed, right? Such that we can apply many techniques, right, in machine learning or into the deep learning techniques, just like object detection and image processing, and in medical domain. So especially in medical domain, at present we are seeing that a 3D view of the internal organs, right, are going to generate, right, with AI techniques, right. So thereby we can visualize AR, VR techniques, right. I can use that. Like that, metaverse is also one of the AI technique, right, where we can examine each and every part of the internal organs, right, by using in 3D technology, right. So like that in robotics, and which are mainly used uh, in the processing technology, automatic process industries, which are needed more number of robotics, whether it is a humanoid or in the industrial robotics. They can use this. There's a lot of demand is there in European countries also. If you go there, their electronic vehicles, they are manufacturing with automatic robotic technology, right? So therefore, we have a lot of techniques in radar and satellite imaging, radar imaging, and they can be used in medical image directly. So like that, we have a lot of applications. Therefore, the advantage of conducting this faculty development program for all faculty members, such that they can learn all these techniques in depth, and also they can do some project works to their knowledge domain. So it will be helpful. Lot of research activities also you can plan, right, by learning the different techniques. So therefore, the experts are from NITs and IITs, so they will give in-depth knowledge on each and every topic, so that the faculty can utilize them and they can improve it, right. So I hope that, and I wish all the faculty members to learn the and gain them from the experts, and it'll make it a interactive sessions so that you can ask a number of questions with them and also get the information from them, right? So one more thing is that attending all the FDPs regularly is very much important, right? So without any break or without any absenteeism, right? So all the faculty members request should attend the FDP program and utilize them and make it a grand success. So thank you very much for this, giving opportunity.
Thank you, sir, for the valuable insights you have given us. I now take the pleasure of inviting our esteemed guest, Dr. B. Rajshekhar Garu, to address the participants. Sir, please.
Respected dignitaries in the meeting, Principal Dr. Y. Mallikarjun Reddy Garu, and Dean of Academics, Dr. K. Giribabu Garu, and HOD of ECE Department, Dr. M.Y. Bhanumurthy Garu, and today's FDP coordinator, Sheikh Riyazuddin Garu, and other faculty members who are present in the meeting are attending this particular FDP. So, good afternoon to one and all. And at the outset, I congratulate HOD Bhanumurthy Garu and the Department of ECE for organizing very meaningful and emerging technologies, whatever we are having as artificial intelligence in the areas of robotics, then VLSI, and then medical domain, as a FDP for 1 week in the online mode for the faculty who are all working in the different places. And I also thank the department and even the college management and the principal for collaborating with the IETE Vijayawada Centre and organizing this particular type of workshops. I also congratulate the Department of ECE for getting the best ISF award for the year 2023 So it's all the efforts throughout the year. Any event will be very enthusiastically, and whenever a particular day or a particular occasion occurs, so the department and even the principals, they will be ready to organize. And I also thank the ISF coordinators for being with the IETE Vijayawada Centre and making that particular events very meaningful and in a very grand way. Then coming to this particular workshop, so which is for 1 week in the online mode. As nowadays we are all looking at this particular intelligence, so where the natural intelligence is dominated by this particular artificial intelligence. And if we just look at a present day industry, so the number of employees, means the persons who are working with the natural intelligence are lesser than the number of people who are having the artificial intelligence. What I want to say is the robots are dominating in that particular industry rather than the persons in that particular industry. So one thing over here is because of that particular accuracy, because always the machine will be having a more accuracy than a particular natural person. So because of that one, so because of the accuracy or the efficiency, so we will be going for that one. But one thing we should remember over here is the natural intelligence cannot be overcome by any particular artificial intelligence. But we should be assured that this artificial intelligence must be taken in a right way, and make this particular robotics, and then in any domain of a medical. Nowadays you can just see even the surgeries are done by this particular robotics under the assistance of a particular surgeon. So all the areas are getting dominated or converted into this particular artificial intelligence. So anyhow, I thank all the resource persons who readily accepted this particular invitation and come forward in spite of their busy schedule to give their valuable knowledge or share their particular valuable knowledge with all our faculty who are attending this particular workshop. So I thank the organizers for giving me this opportunity, sir. Thank you.
Thank you,
sir,
thank you, Dr. Rajshekar.
Thank you, sir, for sparing your valuable time and motivating us. I now request Mrs. Pandana ma'am to give the brief profile of our today's resource person. Ma'am, please. Pandana ma'am. Pandana ma'am.
I think she has not joined. Dr. Riaz, you can go ahead if you have the profile.
Hello.
It is audible. Yeah.
Okay, sir. Thank you very much, Vanilla Madam, for giving me an opportunity to introduce Professor Mrs. Brinda Bhowmick. She is a Dean of Academics, NIT Silchar. Actually, Brinda Bhowmick, Madam, made her BE degree with first class honors and ranked first in Electrical Engineering Department of Regional Engineering College, Silchar. MTech degree with first class distinction and PhD degree in 2014 in microelectronics areas from NIT Silchar. She has qualified GATE in ECE in 2002 with 1530 All India rank. Currently, she is a professor in Electronics and Communication Engineering Department of NIT Silchar since July 2022. She has 20 years of teaching experience. She achieved the Visvesvaraya Young Faculty Research Fellowship in January 2018 from MEITY, MIT Government of India. She has completed one EMR2 project from CSIR entitled Heterojunction Tunnel FETs. characterization, modeling, and simulation of electrical parameters. She has authored 117 SEIE international journal papers, including 12 IEEE transactions, 33 conference papers, 18 book chapters, and published 2 patents, and 3 patents are in granted status. She has authored 1 book, Simulation and Modeling of Emerging Devices, Tunnel FET and FinFET, in Cambridge Scholars Publisher, UK. 8 PhD scholars are awarded PhD degree under her guidance, and currently 7 PhD scholars are doing research under her guidance. Many PG and UG studies have completed their thesis under her supervision. Her research interest is simulation and modeling of various semiconductor devices like TFET, SBMOS, HEMT, FinFET, graphene FET, tunnel diode, including group 3 to 5 materials, 2D materials, and their applications in analog and digital circuits and sensors. She is the reviewer of many reputed journals like IEEE Transaction on Electron Devices, ECE Journal, Journal of Solid State Electronics, Journal of Computational Electronics, IEEE Sensors Journal, International Journal of Numerical Modeling, International Journal of Electronics, Physics Scripts, Silicon, IEEE Transactions on Nanotechnology, etc. She has given invited talks in many TechWhip sponsored workshops, ATAL workshops, and IEEE summer courses also. She was Associated Dean Faculty Welfare from January 2021 to January 2023. From 23rd September 2023, she has been assigned the responsibility of Dean Academics in NIT Silchar, Assam. Thank you very much, ma'am, for accepting our invitation and spending your valuable expertise in VLSI domain to our participants. Thank you, madam. Thank you, Vinila, ma'am. Actually, madam is going to join.
Yeah, thank you for that. And I want to thank inviting me, give me the opportunity to give a talk in your institute. And I want to thank your director, sir, also, and all the participants also. So for organizing the AI-based workshop, which will help all the participants, and they can also learn many things, many technologies, very new technologies. So I thank all of you. Okay, shall I start my presentation?
Yes, ma'am.
Thank you, ma'am. We are very much fortunate that you are with us today. You may proceed the session, ma'am. Thank you.
Okay, thank you.
Brinda, ma'am, now we are going to make you as a presenter. Then please
Yeah,
share the screen. Okay, ma'am.
Yeah, yeah. See the PPT?
Ma'am, have you shared the screen?
I have shared.
Okay. I think net. Yeah, ma'am. It's shared, ma'am. Thank you.
Can you see?
Yes, ma'am. PPT is not open, but your screen is visible, ma'am.
You can see the PPT.
Yes, ma'am.
Brinda ma'am, please click on those three. Okay. PPT is open, ma'am.
PPT.
PPT
Hello?
is. Hello, ma'am.
Visible?
PPT, visible, ma'am. Can you please put in presentation mode?
Yeah, I have kept in presentation mode.
Yes, ma'am. Now it's visible and audible.
Okay. So today we'll discuss about some of the emerging semiconductor devices in the VLSI for sensing application. So these semiconductor devices, why they are emerging? Because using those semiconductors, we can use some scale down options. Whenever we scale, which is required for increased packing density, those semiconductors can be used. Instead of CMOS, we can use some tunnel FET devices, which are basically operated on the principle of tunneling phenomena. So this device can also be used in medical domains. Some biosensor application also it is used, and it can sense some of the gases, and it can be used for energy harvesting applications also. Okay, whether the change of slide is visible to all of you? Hello?
Not
No.
yet, ma'am. Maybe it takes time a little bit. Yeah,
Yes,
it's
ma'am.
it's outlined.
Yes, ma'am.
Can you see the next one?
Yeah,
Yes,
it's
ma'am.
outlined
Yes,
slide.
madam.
Yeah. Okay, though I'm asking because due to heavy rain actually in Assam, yesterday night there was a huge rainfall, and because of that, I think our internet connection is quite affected. Okay, so outline is that introduction to semiconductor device. First of all, we'll discuss. Then we'll discuss advantages of TFET technology, MOSFET versus TFET, band-to-band tunneling, various emerging structures, then overview of AI-based approach. Artificial intelligence-based approach can also be used to optimize the design parameters for the particular tunnel FET. An application of TFET biosensor. We can use TFET as one of the sensing application. Similarly, it can be used in gas sensor also, RF energy harvester, and then in RF energy harvesting, basically we are using some rectifier topologies. Then I'll give you some concluding remarks, and some references are also mentioned. So semiconductor industry is in continually high demand, especially as consumers look for increasingly advanced and feature-filled connected devices. So we want more feature-filled devices that will give you more advanced applications. The increasing demand of semiconductors will necessitate chip makers to put an enhanced focus on typical IoT requirements. Now, nowadays, we are going for IoT devices. So they need some ultra low power and need some security also. So all these demands can be fulfilled by some emerging devices. Introduction to emerging devices continuation. CMOS technology facilitated the development of new logic and memory products in the personal and commercial branches of the computer industry by mid-1990s. Within a decade, however, power limits become an issue. So power is also a major issue. we want to reduce the size, as well as we want to get low power and high speed applications. So all these can be obtained if we use some emerging device. Innovation has continued to drive new semiconductor technology in the present. In order to achieve enhanced performance, the industry has started to depart from past architectures and devise solutions. We want to propose few solutions to meet the present and future needs. So whatever the architectures are available, if we use those things, then we cannot reduce the power and also the cost. Cost is also an important factor, because whatever device we propose, that should follow fabrication methodology, that should follow the standard processing technology, because simple processing technology has already been introduced, and whatever device will follow the similar processing technique, then our cost will be reduced. So a key goal of the research and development is to replace commonly used technologies with new technologies. So we are replacing with some new technologies. So hope to meet the demand for electronically accessible devices that must have high speed, high density, low power, and it should be embeddable, because whenever we develop some system on chip, all devices, all the circuits should be embeddable in a single chip, so that we can save some space area, as well as we get some high speed and low power applications. So we need a device that should provide us steps slow that can be easily used for applications, high on current and reduced supply voltage. Because if we get on current, then supply voltage, then our power consumption can be reduced. High on of current ratio, and we need some unidirectional connection, because fan devices is based on unidirectional connection. Can we get all these properties? If we get, then it reduce the losses. So one of the device is
Okay. So I'll ask
one of the
my colleague
is the TFET device
registered, but because of the timing, we are not. Okay, thank you.
That has emerged as a promising candidate to mitigate the supply voltage scaling challenge. Supply voltage scaling challenge is also a very important thing. It works on the band-to-band tunneling carrier injection mechanism in a reverse biased gated PIN diode. So tunnel FET is nothing but a gated PIN diode with field effect control of the tunneling current. So structure is similar to a PIN diode, but over the channel, one gate structure is available. So tunnel field effect transistor, tunnel FET is nothing but a gated reversed biased structure. Working on the interband tunneling, means tunnel FET basically works on the principle of tunneling phenomena, where electrons are tunneling from source to the channel via the band gap. So that principle can also be called similar to Zener tunneling principle of operation. Zener tunneling is nothing but a tunneling where the depletion layer width should be very small and tunneling window should be small. There only you can get the Zener tunneling principle, and it can operate in both N channel and P channel modes. So you can see the band diagram of N TFET showing the band bending during operation. Okay, you can understand what I'm saying? Participants, hello? You can see the diagram?
Yes, ma'am.
Okay,
It's
so
clear. Yeah, it's clear.
the energy band diagram of a tunnel FET is shown here, where source, channel, and drain is shown, and your blue color is showing, red color is showing the on-state Venn diagram, and red color is showing the tunneling region. You can see electron is tunneling, E is shown with the arrow symbol, where electrons are tunneling from source to the channel, whereas the red color is showing when gate voltage is 0 volt, means it is the off state. In case of off state, there is tunneling is negligible amount, whereas in case of on state, huge tunneling is possible. So tunneling current can be obtained when the gate voltage is increasing. Then we have some ITRS. ITRS means International Technology Roadmap for Semiconductors. So year-wise technology is given from year 2013 to 2028. Future is also projected in this figure. So black color is showing the research required, and our blue color is showing development underway. The pink color is showing pre-production, and yellow color is showing the continuous improvement. So in tunnel FET, what are the improvements we can do? We can use some nanowire MOSFETs. We can use some alternative channel material like group 3,5 periodic table we have studied. We have seen chemistry. Group 3,5 materials can be used as a channel, or germanium can also be used as a channel material. And some alternate channels are also available, like carbon nanotube, graphene. These are also there. So why people are using those materials, new materials? Because they can improve the mobility, they can improve the electrical characteristics of the particular device, and some tunnel FET is also incorporated. Here you can see the tunnel FET can consider all these advantages, and it is research is required and development means still research is going on, and academicians doing lots of research on tunnel FET to improve their capability. Tunnel FET, I have the current is dependent on the electron tunneling phenomena. Tunneling phenomena is basically nothing but based on tunneling probability, which is proportional to the drain current. Now you want to increase the current. If you can improve the tunneling probability, then only the current, the on-state current of the device can be improved. So research is going on because the tunneling current is very low. In order to improve the tunneling current, various research is going on based on different materials, based on different gate engineering. Means we can use different high K gate dielectric, we can use tag gates, we can use hetero gate. All these options are given so that improve it on current. Why we are going for tunnel FET? Because of the fact that in tunnel FET, the substitution swing is very less. The substitution swing is less than 60 millivolt per decade. That indicates that its switching property is very good compared to conventional CMOS devices. Yes, it is, and also another advantage is that it can operate at low power, and impact of temperature, impact of self-heating on the tunnel FET is also low. So tunnel FET has come to the research. People are doing research, and still all academicians, some of the people have fabricated tunnel FETs, various structures of FET, and it has been found that its digital application as well as analog circuit applications and RF applications also tunnel FET is applicable. Then we have ITRS targets for on and off current. Here the graph, there are two graphs. Left hand side graph is corresponds to the off current, and right hand side graph is corresponds to the on current, saturated current. Now here the red color is showing low operating power, that is for tunnel FET, and low shadowing power, and 5 is shown by red green color. So from this graph we can see that tunnel FET is almost in the middle range. Tunnel FET off current is much higher than the low standby power cases, but it is lower than the group 3,5 material. Whereas the figure is showing that the tunnel FET performance is the red color, that is higher than the low standby power. That is less as well as high performance devices. So from this graph, we can conclude that tunnel can be promising because its off current can be reduced and its on current can be increased. If you use different channel materials, you do some source engineering, if you do some gate engineering. So tunnel can be a promising candidate to consider it in the future because the graph is plotted for the projected year of 2025. We have IRDS roadmap, international roadmap for devices and systems. It's showing combining SoC and system in package. System on chip and system in package to consider. Then what you can see, as we decrease the technology from 130 nanometer to 22 nanometer, if we reduce our technology node, means if we increase our packing density, then systems and combining both system package, so higher value systems can obtain beyond the technology devices. We can use some other emerging devices. This IRS roadmap is showing the future production. Is in future, if we reduce our technology node, what are the possibilities? What are the applications also mentioned here? Then receives and high voltage power sensors, actuators, and some biochips. If we want to make that, we will go for VLSI devices that will be giving you better applications as a logic circuit, so that we can apply it different biochips sensor applications. So this is the IEEE international roadmap as well as for the design of the systems. Initially, ITRS developed after 2020. It has an idea of integrating devices which for future. So we have discussed the future of our device using ITRS and IRDS projections. Now we can compare tunnel FET versus MOSFET operation. In case of MOSFET, we can see the electrons. There are both the sides are N plus, whereas TFET is a asymmetric device. So P plus and N plus regions are there. Okay. So what we can see here, with the whenever we get to source voltage, then in the MOSFET, the barrier is reducing. Barrier between source and channel is reducing, whereas in case of the tunneling junction is reduced. So see figure, the blue dots, the green dots representing the electrons are tunneling from source to channel. As we are increasing the source voltage, the tunneling is reduced, and therefore electrons can tunnel from source to the channel. Okay, so have you seen the tunnel FET this operation? So I think I have seen Venn diagram, and you can understand the difference between the MOSFET and the tunnel FET. Unlike MOSFET, the controlled tunneling window in FET is able to effectively filter the high energy carriers in the energy bands, as leads to sub 60 millivolt per decade steep slope at the room temperature. So TFETs can provide you less sub 60 millivolt per decade steep slope. In order to achieve the projected energy efficiency benefits, a desired tunneling current at the device on state, a high on-off current ratio, and an average SS over a few decades of current change are the key differentiators. So since current is low in case of tunnel FET, in order to improve the current, various researches are done, and high on-off ratio is desirable, and steep SS is also an important factor for the design of tunnel effects. So these are key parameters for design of tunnel. We can band in funny distribution. Figure 7a shows NIN MOSFET and figure 7b shows PIN effect. In effect, high energy part of the source, you can see the figure A, high energy part of the source. Distribution is cut off by the band gap region, and it leads to 16 volt per decade. Phonon-assisted tunneling becomes important under these conditions. So in this case, phonon-assisted tunneling also takes place, which is a very important phenomena. And whatever tunneling takes place in case of tunnel fact, it is nothing but a band-to-band tunneling, because tunneling occurs from source to the channel, which is ordering from the source valence band to the channel conduction band. For band-to-band tunneling to occur, an electron in the valence band of the semiconductor tunnels across the band to the conduction band without the assistance of traps. Here, no trap has been considered, direct tunneling has been considered. The band gap acts as a potential barrier that the particle tunnels across. An electron that travels from the band to the conduction band without absorption or emission of photon in direct tunneling. A tunneling particle for the condition that is here. A tunneling momentum by reaching in direct tunneling process. So direct so indirect semiconductors, gamma they are direct band gap. Energy band gap in process. Visible in indirect band gap case. So direct tunneling process is very less. It is not common because of transmission probability is typically with the increased barrier height. So the transmission is very late. Direct tunneling is also very less case real light. The most probable path is the smallest barrier. For direct tunneling, the requirement for conservation of particular momentum, that is another causes an implicit tunneling. So always for direct tunneling, the perpendicular momentum should be conserved. A particle perpendicular momentum in valence band must tunnel to state with the same perpendicular momentum in the conduction band, which results in a longer tunneling path. So in order to conserve the perpendicular momentum, the tunneling path may be a long tunneling path. So that the electron a longer tunneling path if it has maintained the perpendicular momentum conserved. In that tunneling process, the phonon does impart or absorb change in the momentum of the particle. So in the tunneling process takes place where the phonon is responsible for changing the momentum of the particle. So that is the difference between the direct and indirect tunneling process. The electron phonon interaction of the indirect tunneling process decouples the perpendicular momentum of valence band and conduction band. So what happens? So the indirect tunneling process, it will decouple. It will couple the perpendicular momentum. An electron in valence band state in the conduction band such that energy and perpendicular are conserved. So most of the cases we can see that the energy and momentum always remain conserved when tunneling takes place. Here, the band gap is shown. Band for direct tunneling, band gap is very high. You can see figure 8, band structure of silicon showing direct and indirect tunneling. Because in order to understand the tunnel FET, the concept of direct and indirect tunneling is very important. The set shows the first brilliant zone for an FCC lattice with points of high symmetric indicated. So what we can see here in the figure, if it is direct tunneling, the band gap is quite 2.4 electron volt. But if it is indirect tunneling, that is phonon provides momentum, band gap is 1.12 electron volt. So direct and indirect tunneling concept is explained with the help of the silicon band diagram. Several lines are shown. The red color is showing the heavy hole, and the black color is showing the conduction band distribution. And we can see tunneling takes place from the valence band to the conduction band via direct path or via the indirect tunneling path. In case of an anti-FET, applying positive. So now we are discussing about the principle of operation of the TFET. Applying positive gate voltage, pushing the energy bands downwards in the channel, resulting in narrower energy barrier between source and the channel. So, but how it can operate? If we apply, there are actually 3 terminals, source and drain, similar to your CMOS. CMOS is having another substrate terminal also. So here, if we apply some positive gate voltage, then your bands are pushing downward, and this allows the electron in the valence band of the source to tunnel through the barrier to the conduction band of the channel under the influence of positive drain voltage. Source. FETs attribute to a low subthreshold swing. That I already told you. The advantage of tunnel FET is that it is giving you low subthreshold swing and tunnel FET. That is very nice and good compared to CMOS. That is the static part. Next, by controlling the of the using the it is possible to switch on tunneling. The PCB depends on transmission with the intermittent tunnel variable. So that is an important which controls the current. That expression to that can calculate it maybe sufficient. Shape with respect to the distance. If the variation of potential with respect to the distance is very slow, then only we can apply the WKB approximation. And it has been seen mathematically, it has been derived that the tunneling probability is proportional to the factor effective mass denoted by Einstein. EG denotes the band gap of the semiconductor. Lambda is the screening tunneling. Q denotes the charge of the electron gate. Energy range del phi is representing the energy range over which tunneling occurs. Designated by del phi. H is the reduced Planck constant. Planck constant is H. H by twice pi is represented here. That is the reduced Planck constant. So what you can conclude from the tunneling probability is that if our band gap is because it's to be dominant, if the gap is smaller, then tunneling probability can be increased. If our lambda is smaller, screening length is smaller, then our tunneling probability can be increased. So in order to get enhanced tunneling probability, we can optimize all the parameters. We can choose different methods. different group 3,5 material, different 2D materials, which are graphene, carbon nanotube. This can be used in order to modulate the T. Next, we can see band diagram. Here again it is shown. Del phi, the parameter del phi is shown, and it is already explained. So lambda is the screening length. Source, channel, drain is shown in the figure. EC is the conduction band. EV is the valence band, and EF is the Fermi energy level. So on state, you can see in on state and off state band diagram is shown. In the on state, there is flow of electron from the source to channel, but in the off state, as we are applying gate to source voltage is equal to 0 volt, in that case, the band diagram is quite wider and no electron can tunnel from the source to the channel. And that is why we can say during the off state, the current is very small, off current, because in case of tunnel FET, what we get? We get the off current is very less. Why you are getting less off current? Because of this effect. That is, the tunneling probability is quite low during the off state of the device. The band-to-band generation rate in tunnel is expressed as GB2B is proportional to some constant parameter e to the power square. Electric field depends on electric field. EG is the electric field and the exponential factor also. So band-to-band generation rate is after time is electrons generated and current is proportional to the band-to-band generation rate. So band-to-band generation rate is a very important factor in case of tunnel FET. Okay, so what factor it is depending? The electric field and energy band gap are the two major factors at band-to-band generation rate is depending. Now, conventional tunnel FET disadvantages. For your conventional tunnel FET is a simple PIN structure with a gate, then its on current is less compared to current obtained for conventional MOSFET. So the disadvantage that I already told you, because tunnel FET current is dependent on the tunneling probability, and tunneling probability is very low. Then tunneling probability is low, and in case of tunnel FET, since tunneling probability is low, the drain current is also low because the current is to the on current. Therefore, in order to improve the on current, we need to do various changes. Some material can be changed, gate engineering can be done, source engineering can be done, and it has higher threshold voltage also, a low off current ratio because off current is high, on current is also low. Switching speed of the TFET is lesser than that of conventional MOSFET due to increased Miller capacitance. What is the Miller capacitance? Miller capacitance is nothing but the capacitance between the gate and the drain, which is coming into the whenever you design a circuit, whenever you consider the analog circuits, the Miller capacitance is coming into the picture. If Miller capacitance is quite high, then switching speed of the device will be affected. So, in all these disadvantages can be mitigated. You can do some research. People have done already some research on that, so that on current can be increased, threshold voltage can be reduced. So, is there any question? On current is less, so we want to improve the on current. Threshold voltage is high. We want to improve the threshold voltage. We want to improve the on state current, and we want to reduce the Miller capacitance. Miller capacitance is a capacitance which is coming between the gate to drain voltage. Sorry, gate to drain terminal CGD. Between gate to drain, that capacitance is known as the Miller capacitance. And Miller capacitance, if you reduce, then the performance of the device can be increased. Now, all of you have seen. So till now we have discussed the advantages and disadvantages of the device, of the emerging device, and how we can get better options. So already I have told you the device which we are using. Now, no device has complete advantage. Some of the devices have some disadvantage also, but how to overcome those disadvantages? In case of TFET technology, there is some disadvantage that I have shown. So in order to overcome those disadvantages, we are proposing various types of architecture. People have done various research using various structure modification, some of the parameters on current threshold voltage and Miller capacitance, all these can be improved. So various TFET architectures, now I will show you in order to improve all these characteristics. So first example is your lateral and vertical tunnel FET structures. So all of you see, now this is a very good research area. People are doing nowadays very good research in tunnel FET and vertical tunnel FET structures. So you can see in case of lateral tunnel FET, the source, channel and drain, and electrons are tunneling along the parallel to the interface. What is the interface? Interface is something about interface between gate oxide and the channel. So electrons are tunneling parallel to it. So they are known as lateral tunnel FET. And vertical tunnel FET, you can see electrons tunneling is shown by the red color. The electrons are tunneling from the source to the channel vertically, which is vertical to the interface direction. So lateral and vertical diagram is shown in the figure. Red color is showing electron tunneling and blue color is showing the drift diffusion. Means after tunneling, some drift diffusion phenomena is also taking place in the device in order to flow the device to the channel. So difference to see direction. Direction is opposite. In case of lateral one, the electrons are tunneling from left to right, and they are parallel interface direction. In case of vertical, electrons are tunneling upward, means they are perpendicular to the interface direction. To be heterogate SY tunnel structures. Next is your heterogate structure, where people are using source, channel, and drain. And you will see on the drain side, the white oxide is upward, increased upward, but it is enhanced. Some part of the white oxide has entered into the drain region also. So what is the advantage of the structure is that here the graph is shown, 11B. It is showing SY in drain, SY in channel, and SY in source. Three graphs are compared. SY in source is very bad, but SY in channel and drain, we can see in SY in drain, the off current is less, whereas on current is more. Whereas SY in channel off current is quite high. So the SY in drain is a better structure. SY in drain is in this black color graph is showing SY in drain structure. So it is better. The discussion is better. You can see here in structure, the on-off ratio has improved. Current is improved. Threshold voltage of the device is also improved. The surface roughness scattering in the source channel is increases as compared to the drain region. This is due to the fact that peak electron concentration here, what a peak electron concentration is available, electron concentration is available at some distance that is beyond the drain. And accordingly, peak electron concentration occurs in the tunneling region. Hence, overall channel mobility is not critical in this case. The ratio is achieved in the raised barium oxide drain. So the structure, why it is named raised barium oxide? Because barium oxide is also a oxide, insulator oxide available just below the channel material. Apart from the oxide is increased, that is why it is known as the raised barium oxide structure. I think all of you have seen the structure and is giving some good over the conventional device. Next, the energy band showing band bending at the tunnel junction. So here, tunnel barrier width is plotted with respect to gate voltage. So what you can see, the tunneling barrier width is compared for IETE effect, means HG means hetero-gate. Remember that HG represents hetero-gate effect, and blue line, dotted line, represents only high-gate effect. So what we can see, and green color is showing the tunneling path. So we can see for HZ effect, the tunneling barrier width much lesser as compared to the high K only effect. Means barrier width can be reduced if we use heterogate. Heterogate means a gate which is consisting of both high K as well as low K effect. High K means high dielectric constant, and low K means low dielectric constant. Why it is like that? It is like that because when you are considering high K gate dielectric near the source, the controlling of the channel of the tunneling will be more. But whenever we are using low K dielectric near the drain, the controlling will be less. That will provide less of current. So our requirement is that we want high on current and less of current. So when it will be possible? When high K gate dielectric is used near the source side, and low K gate dielectric should be used near the drain side, because high K gate dielectric is having higher dielectric constant. That higher dielectric constant will give you higher gate capacitance, and it will control more the channel as compared to the low K gate dielectric. Next is the heterojunction structure. So I am showing different structures that are designed or that are fabricated and simulated by the research, so that the characteristics of the tunnel FET can be improved. As you can see, heterojunction is used. SIG heterojunction is used at the junction. Silicon source is P plus type, and silicon is P type channel, and silicon drain is used, and over the channel you have gate dielectric and gate. So SIG, what is SIG? Have you heard SIG? SIG is nothing but silicon germanium compound material that is added in the channel source junction, so that it can modulate, it can change the band gap, as well as it can change the relative dielectric property, and it will provide more tunneling probability. If tunneling probability from the source to the channel is more, then you can say, if the tunneling probability is more, then you can say that tunneling current is the obviously the drain current for the device will be enhanced. So this is nothing but a heterojunction structure. Why it is hetero? Because silicon and SIG, they are forming hetero structure. Next is the effect of germanium mole fraction on the on current. Since we have used SIG material and germanium is giving you a germanium mole fraction control. If you control the germanium mole fraction from 0.2 to 0.8, then you can see the on current is high near about 0.3 germanium mole fraction. Then after that it is reducing. So germanium mole fraction has a good impact on the on current control. So last figure, that heterojunction structure that shows the germanium mole fraction control can have impact on the on current. And hello, do you have any comment? Any? Okay. So can you see? Then we have the energy band diagram. The availability of the carriers on the source side to tunnel through the barrier is expressed from here. We can see the level, that is conduction band, valence band, electron quasi-Fermi level, whole quasi-Fermi levels. So these whole quasi-Fermi levels, electron quasi-Fermi levels are plotted for different mole fractions. Okay, so energy band diagram based on germanium mole fraction is shown. And we can see at 0.3 mole fraction, the tunneling barrier is very small. So that diagram indicates that at 0.04 length, the energies are coinciding. It shows that the tunneling probability will be more at this mole fraction. Then we have some NPN TFET structure. Structure is consisting of another pocket, N minus pocket. So a tunneling junction is formed between the P plus region and a fully depleted narrow N layer under the gate, which reduces the tunneling width and creates local bending. So what is the function of the N pocket? It will reduce the tunneling width and steep substitution swing is obtained. At the same time, provides high on current as compared to TFET. So PNP TFET structure is another researcher has designed in order to get improved electrical characteristic. Then we have some circular gate TFET structure. You can see the gate drain proximity is a cause of ambipolar current in TFET. So by changing the gate radius, here the gate structure is like a circle, half circle, we can say semicircle. By changing the gate radius, both the dielectric thickness at the channel junction as well as ambipolar current can be reduced. So this structure, the yellow marked portion is showing the tunnel junction for VTBT, this bend-to-bend tunneling has less dielectric thickness. And ambipolarity. What is an ambipolarity? When a negative voltage is applied to the gate, VTBT current can also flow. VTBT means bend-to-bend tunneling current, which is defined as the ambipolar state. The difference between the on and M state is the position where VTBT occurs. In ambipolar state, unwanted VTBT occurs between the channel and the drain. This ambipolar behavior is that the TFET is turned on even when it is expected to turn off by applying the gate voltage. So ambipolarity limits the feasibility and applicability of the TFET. So this is nothing but an unwanted function which can be reduced. So whatever current is flowing, whenever you are applying a slight negative voltage, you have to reduce it. So in order to reduce this circular gate structure is giving you less ambipolarity. Then we have showing here the gate drain underlap effect. Using gate drain underlap reduces the output drain current, which is detrimental to circuit applications of the devices. With gate drain underlap of 0 nanometer causes the current, which reduces and the gate drain underlap increases. The graph is showing the comparison IDVG graph transfer characteristic for circular gate and for TFET. It has been found that for the circular gate structure is much better than the TFET because ambipolarity can be more reduced for the circular gate structure. Then we have gate on channel TFET. Now you see gate structure is modified. 15 nanometer in the structure you see 15 nanometer gate underlap is given and gate is moving towards the source side so that coupling of the source will be better and it will improve current and better. So this is the structure of a gate on channel TFET, which provides you better ambipolar current, better iron of freedom, just by providing 15 nanometer gate drain underlap. Then we have germanium source vertical TFET. So germanium source vertical TFET, you can see the yellow color, the cross-sectional view of the germanium source vertical effect, tunnel field effect transistor is shown. The yellow color is representing the source. The blue color is showing the green color as drain. So this is but because tunneling takes in vertical direction from source to the channel means from yellow region to the green region, tunnel takes place vertical direction. So it is a germanium source vertical TFET. So what is the advantage of the structure? The advantage of the structure is that if you use this type of structure, the tunneling probability can be enhanced, as well as ambipolarity can be reduced, and threshold voltage can also be improved. Next, we have the on-off current for the particular device. So you can see the graph is compared with respect to silicon thickness and on-current ion-off ratio. So the current which is shown is showing by the green color, red color is showing off current, and blue is showing on-off ratios. Now we can see with the increase of silicon thickness of the silicon thickness, this is the thickness of the body of the device. With the increase of the thickness, the reducing, but the ion ratio, which shown in the blue color, ion of ratio is reducing, whereas on current is also reducing, but off current is increasing. So it's that if the silicon thickness is quite near 1 nanometer or less than that, then only we can get better on current, better off current, as well as better on off ratio. So the variation of ratio is also varying with respect to the silicon thickness. Then we have a very interesting structure. All of you can see, because nowadays optically gated tunnel FET structure is also used. Till now we have discussed different structures, but now this structure is quite different from the other, because it can act as optically gated tunnel FET structure. So what you can see here is that the gate is quite wider, where incident photon flux is incident, and your source, channel, and drain are shown in the figure. You can see the structure. Source is there. In the source, you have germanium pocket and plus pocket. Then you have a channel. Then you have a drain. So the incident flux is flowing, and you can get some changes in the current of the channel. If you measure the current, then optically incident photon flux is falling on the gate metal, and metal gate will give you influence on the drain current. So drain current variation shows that the TFET structure is based on optically gated phenomena. So these type of structures can also be used. TFET can also be used in case of optical sensing applications. That is a very new application. People are doing research recently in the year 22-23. People have done, and there's an optical gated application of the tunnel FET structure. So till now I have discussed the principle and various structures of the tunnel FET that will give you better options for electrical conductivity, electrical current, drain current, threshold voltage, ambipolarity, then ion of ratio, subthreshold swing. So all the parameters can be modified and can be improved in all these structures. And then I will show you just in optical generation. Device optical generation in the gate region, electric voltage generation. Those electrons having energy greater than the band gap of the silicon will move from the valence band to the conduction band of the gate region, leading to a phenomenon called photogeneration. So energy should be greater than the band gap. That is the main factor, main cause, or main condition for the photogeneration. What is the condition of photogeneration? Energy better than the band gap, that can only give you photogeneration. The movement of these photogenerated carriers inside the gate controlled by the applied gate bias. So the photogenerated electrons can be controlled by the application of the gate bias. Next, so till now I have so this presentation actually divided into first part I have shown you. Now first part is over. First part I have shown you different structures, TFET based structures, emerging structures, tunnel FET based structures will provide you various good, better electrical characteristics as compared to the conventional CMOS applications. Now I have come to the overview of AI based approach, AI based artificial intelligence based approach. So TFET can be simulated using the TCAD software, Synopsys TCAD software, as well as these simulation. You can people have created many devices, but some artificial intelligence based approach nowadays people are doing research. Earlier research was only done based on the TCAD approach. Now some AI based approach has also come into the picture. So we have the big data. All of you know what is AI. AI big data is structured and structured data used as an input to build or train AI or ML algorithms, machine learning algorithms. So artificial intelligence and machine learning have some common area, and artificial intelligence machines with seemingly human capabilities. Deep neural network, one type of machine learning that uses vast amounts of data to perform AI tasks. And machine learning provides you basically the computational and statistical tools, some of which are also used for AI cases. So we want to show you how AI-based approaches can be used for event design. Machine learning has grown in popularity as a result of the virtually infinite amount of data available, affordable data storage, so why it is used, and the development of less expensive and more powerful processing. So machine learning data can be used because they have the more powerful processing. Many sectors have recently begun to construct more machine learning models. These models analyze larger and more complicated data, more data sets, and offer faster and more accurate findings of data. More accurate finding can be one of the most applications of data is that in case of data, we are optimizing the we are optimizing the different parameters. Threshold voltage, then subthreshold swing, Ionov ratio, Miller capacitance. Then we have the on current, off current. So all these parameters are related with scaling also. That's simple thickness. I have simple thickness. Then we have the all these parameters can be given to machine learning tools. And the machine learning tool, what they will provide, they will give you the optimized results. And based on the optimized results, we can design a particular tunnel fit which gives it the best predictions. Modified to be the best technique, construct models, strategize, plan for industries that rely on and next step to investigate it rapidly and effectively. To devise targets, many of current impact has been created in the semiconductor device manufacturing industry. So nowadays we are using a very impact in the industry because people are doing say using particular technology node, say 22 nanometer technology node. In case of 22 nanometer technology node, the different lengths are already defined within a range. Say gate length is defined, device oxide length is defined, oxide, gate oxide length, then we have channel length, then we have silicon body length, then doping, every parameter is defined within a range. But in order to choose a particular in case of PCAD, it is very difficult. That is why people are semiconductor industry nowadays they are handling a large amount of data in order to get a optimum result, in order to get optimized value of all these parameters. Nowadays, artificial intelligence techniques can be used. The rapid expansion in computational and storage capabilities of IT systems, advances in machine learning and artificial intelligence demands improved because optimum results use that also give you improved efficiency and operations. So nowadays people are using various types of techniques. Certain difficulties include scaling. Already scaling, if a scale devices and maybe disadvantages, heterogeneity of data, short channel effects, because devices when you reduce, there are various short channel effects like visual loading, like channel length modulation, threshold voltage roll-off. All these are known as short channel effects. Tunneling effects, some of the tunneling effects, gate tunneling, that is an undesirable effect. And device variability, some of the variability effect we can see due to the grain size, metal grain size variability will cause the deviation of threshold voltage, deviation of on current, must be addressed. So all these parameters if you want to address, you can based machine learning based solutions in the semiconductor manufacturing industry. That is why it's critical to discuss and comprehend the optimal devices. That is why it is very much critical to comprehend the optimal device designs and trade-off among numerous design goals, such as natural length, vertical electric fields. So all these goals we to reach. Some value of vertical electric field. So all these very difficult to, because some of the parameters you improve, there may be degradation from other parameters. So in order to improve everything, we cannot say that all the parameters we can optimize almost at the best level, but some of the values are also existing with some design goals. Multi-object oriented programs has a foot in a variety of engineering sectors. A rule-based fuzzy classification method can also be used for predicting fuzziness based on environmental conditions. A multi-objective selection approach is also available. Non-dominated sorting genetic algorithm, that is NSGA2, and also another option to perform analysis using various parameters of tunnel effect, using machine learning methods, a multi-objective optimization, because whenever you want to design a tunnel effect, you need a multi-objective optimization technique, because various parameters are available and you want to optimize various scaling parameters, various physical parameters, lengths, then gate lengths, oxide thickness, all the parameters should be optimized at a time. And by keeping other parameters within a range, because you should know at which range the parameters will exist. And these are the various machine learning tools available with a multi-objective optimization framework for 2D materials transistor, because nowadays people are using 2D materials, need scaling in it. So scaling limit is because we want to scale we want to overcome effects like fuzzy logic system, sorting, genetic algorithm, and any other methods also people are using in order to get optimized electrical parameters with simultaneous optimization of physical parameters. That is the most important aspect of designing a tunnel effect. Okay, so this part is showing you how ML-based techniques can also be applicable to optimize the parameters of the tunnel effect. Multi-objective optimization device design that combines rigorous physics-based modeling. Okay, so we have some modeling parameters utilizing the parabolic approximation method with machine learning techniques to solve the problems of constructing nanoscale transistors. So in order to construct nanoscale transistors, we need to use some of the mathematical approaches, parabolic approximation, along with some machine learning optimization technique. The non-dominated sorting genetic algorithm is a genetic algorithm that is done by doing gradient-free efficient global optimization on several tunnel effect design goals. Already people have done. The main objective is to develop the optimization technique to find the design targets of the tunnel effect. I already told you. So optimization techniques you will apply so that you can design various tunnel effects with the electric parameter and with the physical parameter. Now, how do you verify? How can we verify those things? So after doing the design optimization using AI tools, we can verify the results from the experiments. We can verify the results from ticket tools, because synopsis ticket tool is a very strong software that is available for doing research in field effect area. So why you are doing for AI technique? Because AI techniques will save your time and will give you a best result. That's why the AI-based techniques are applicable to the design of tunnel effect also. Now, till now we have discussed about I discussed the principle of tunnel FET emerging device. Then I have showed you various structures. What are the structures people can use? Then next I told you about the AI-based techniques which can be applied to the TFET design, optimization of TFET design. And now I have started the application of TFET as biosensor. So you can see the biosensor application. So biosensor application, I'm showing application of TFET is biosensor. So what is actually a biosensor? Sensor, obviously, all of you know what is a sensor. A sensor converts physical quantity into a signal which can be read by an observer or an instrument. A sensor that integrates biological element with a psychochemical transistor to produce electronic signal proportional to single analyte, which is then converted to a detector. So what are the analytes used here? They are target biomolecules like protein, toxin, peptide, vitamin, sugar, metal ion, pathogen, pesticide, various biomolecules we can use. And these molecules can be detected by your biosensor. So basic principle of biosensor, you can see biosensing principle, analyte, receptor, molecular recognition, then transducer, then measurement, data recording and display. So what are the uses of biosensors? These are used by clinical diagnostics, food and agricultural processes, environmental monitoring, because sometimes we want to monitor what is the amount of water, soil, and present in our environment, detection of warfare agents, and crime detection. In case of crime detection also, some biosensors, because level of pH, level of these things also we can measure using with the help of biosensor. Application of TFET, FETs as a biosensor. An innovative research perspective in terms of design, parametric studies, and analytical modeling. FET-based biosensors are gaining interest due to their compact sizes, prevalent manufacturing process, label-free detection. That is the most important thing. Label-free means no receptor is used. And without any receptor, directly the gate dielectric can sense in the dielectric, gate dielectric portion can be etched, and in the empty area, the biomolecules can be entered and the device can act as a biosensor. However, the need for miniaturization of transistors has led to the emergence of novel devices that can withstand the degradable effects of downscaling. One such novel device, tunnel effect transistor, which unlike MOSFET operates on the principle of band-to-band tunneling and therefore offers low leakage currents and current research. So people are doing research. They have developed the electric modulated FET, and then nowhere tunnel FET is also been developed, and some partially filled nanogates also made so that it can be occupied by the biomolecules. So different structures people have developed. So what is the basic working principle of label-free dielectric biosensor? A portion of the gate, that is very important application. Nowadays, it is a very good research area. People are doing by medical application. How we can apply our devices in some medical application. A portion of the gate dielectric material is etched out. Now, how it has been done? A portion of the gate dielectric material is etched out to form a nanogap. When biomolecules are immobilized in the nanogap, the dielectric constant of the gap changes. A change is reflected in the drain current and gives better sensitivity. This action is carried out in the simulation process. So always can be shown experiment solution by considering an insulator having the same dielectric constant as that of the biomolecule. With types of proteins have unique dielectric constants, such as biotin, streptavidin has dielectric constant 1. Charged amino acids having dielectric constant in the range of 11 to 25.6. Gluten, keratin, these have dielectric constant in the range of 5 to 10. The area of nanogaps which are not occupied by biomolecules are filled with air. So biomolecules are occupied gate dielectric, and their sensitivity can be measured. So here in structure, in this presentation, structures are shown: circular gate and heterojunction TFET biosensor. So here sensitivity has been measured. Sensitivity, how it is measured? Two currents are taken, IDK and IDAR are the drain currents of the FET, where nanogap is filled with biomolecule and the nanogap is filled with air respectively at fixed gate and drain voltages. And you see the red color biomolecules which are shown in the figure. The biomolecules are occupying the nanogap for the biosensing. For two devices, it has been done, and it has been compared that which device is providing you better sensing capability. Now you can see the impact of negative and positively charged biomolecules on the sensitivity. So sensitivity can be measured for both the devices. One is circular gate structure defect, I have already shown. Another is heterojunction defect for both the charged, positive charged and the negatively charged biomolecules. So we have seen that since biomolecules, how we have introduced, biomolecules are introduced in the gate oxide area just by changing their dielectric constants from 1, 5, 7, 10, and 12. And it has been seen that as the dielectric constants are increasing, the current, the drain current is increasing. The sensitivity is observed to be decreasing or increasing in both biosensors with negative or positive charges of the biomolecules are occupying. So when biomolecules are negative, sensitivity is decreasing, but when positive biomolecules are used, the sensitivity is increasing. Decrease or increase is responsible for increase or decrease of the drain current. If we increase the drain current, then sensitivity will increase. If the drain current is reducing, then the sensitivity will be reducing. So we can see comparison with MOSFET based biosensor. So here two figures are shown. Sensitivities of circular defect, HJ defect means heterojunction defect, and MOSFET. Here three defects are compared with the various dielectric constants. But dielectric constants are varying from 5, 7, 10, and 12. So not only does it shorter channel length, but affect the electrical characteristic of a MOSFET. So for whose the sensitivity is highest? We have seen the sensitivity for the CJ, means for the circular defect, is highest as compared to the heterojunction and as compared to the MOSFET. Why? Because in case of CJ defect, the tunnel junction is more widely controlled, more controlled by the gate. And that is why the sensitivity of the circular gate defect is found to be highest for different biomolecules. Biomolecules may have dielectric constant 5, may have dielectric constant 7, 10, and 12. Now, next slide. In this slide, we are considering different non-ideal cases. So biomolecules are, whenever they are entered into the empty of gate dielectric, there may be some non-ideal issues. Non-ideal issues are very important because those non-ideal issues will be available only when we do the practical cases. But in case of simulation also, in order to make it authentic, we have to consider some of the non-uniform hybridization cases. One of the non-uniform hybridization is steric hindrance. Practically, the fully filled nanogate is rarely encountered. After the hybridization biomolecule, it initiates the nanogate and continues for a period of time. The already hybridized biomolecules hampers the entry of more biomolecules. This effect is known as steric hindrance. When some of the molecules are entering, they are not allowing more biomolecules to enter. This effect is known as steric hindrance and results in non-hybridization of various profiles of occupancy along the nanogap. So we can see how the molecules are adjusted. Convex, concave. Figure A is showing decreasing. Figure B is showing increasing. Figure C is showing concave, convex, and concave, and figure D is showing convex profiles. So various profiles are showing. These profiles are nothing but the way how the biomolecules are entering the space provided by them. So we can see different field factors are also considered. Field factor 32% is considered and field factor 58%. Field factor means how much area of the gate dielectric is occupied by the biomolecules. So case one is 32%, for which decreasing profile has the highest sensitivity. And to one, the graphs should be 50%. All of you see the profile mentioned. One is decreasing, another is increasing, and convex profiles. Out of the 48%, the concave profile and the decreasing profile has the highest sensitivity. What is the reason behind it? If we can analyze some of the graphs, but what is the reason behind it? The reason that in case of decreasing profile and in case of concave profile, the more biomolecules are existing near the junction. Since more biomolecules near the tunnel junction, the drain current will be more for that type of configuration, that type of size. That is why, since more drain current we are obtaining, so more drain current will give you more sensitivity. And that is why we get for the decreasing and for the high sensitivity more. Next is the non-ideal issue. That is the position of probe on sensitivity. The degree of hybridization of probe and target molecules depend on the location of probes, means where probe we are placing. The sensitivity in each such cases is dependent on how the probe position influences the operation of the sensor. So probe position is also an important factor that also impact the sensitivity. This table here, one table is shown. The table lists different cases of probe placement inside the nanogap, both for circular defect and for heterojunction defects, and lists corresponding sensitivities in each case. Sensitivity is more when the probe is placed near the tunnel junction. Here also similar cases are shown. And the total tunnel length, nanogap gap which is kept free for biomolecule is 25 meters. The sheet area represents the biomolecule occupancy. So there are total 9 cases were considered. Case 1, case 3, case 4. Case 1 corresponds to 50% for the nanogap. Case 2 corresponds to 50% nanogap. For case 4, 30% nanogap. Case 4, 60% nanogap. Similarly, is occupied. So 9 cases have been considered considering the probe placement. So CJT FAT and HJT FAT has been measured, has been compared in terms of their sensitivity, and it has been found out that for the CJT FAT, the sensitivity is 10 to the power 6. For case 4, 8.6 into 10 to the power 6 for that will provide better sensitivity where no capital 6% and for bio electric cost. So is for circular it also having a great impact. So this is also another issue.
Hello.
Okay,
Hello,
so
Brinda madam.
Yeah.
Brinda ma'am, can you please put it presentation mode, ma'am?
Okay. Just
Then it can be visualizable.
Okay.
And somewhat voice is breaking. If you can stop the video share video, then the voice quality
Yeah,
may
yeah.
be. Yes, ma'am.
Application of TPET structure as a gate sensor, as a gas sensor. Now it's okay. Hello.
Hello, ma'am.
Hello. Now it's
Hello,
okay.
ma'am. Voice is okay, ma'am. Please put
Okay.
in presentation mode.
Yeah, I have kept it in presentation mode.
Okay, okay. Maybe little bit delay. Okay, ma'am.
Yeah. Heavy rain.
Okay, okay, ma'am.
Okay,
Okay, okay, ma'am.
rising.
Okay, ma'am.
Sensors are devices. So as I have shown you the sensor application, I am showing you the gas sensor. Gas sensors are devices used to detect and identify a different type of chemical compound. Commonly used as a device to detect and gas concentration. So the applications, gas sensors are very important. Detect air, industry, application, and detect harmful gases in mines, environmental monitoring. Gas sensors measure the concentration of gas in its vicinity. Gas sensors react to the gas at its concentration. Each gas voltage that is field at which it is analyzed. Sensor identifies gases by measuring these voltages. The concentration with time measuring the current discharge in the device. Object devices can also be used as a gas sensor application. For the ribbon, based sensor is this here. Carbonyl tropographic ribbon is employed in the material instead of conventional material such as silicon and germanium. Silicon and germanium, we are using some conventional material, graphene nanoribbon, due to their electrical and mechanical properties. Vertical structure reduces parasitic capacitance effect due to detached of the channel from the substrate. And from the fabrication point of view, vertical defect is easier to implement conventional defects. So vertical defects, because they are easily fabricated and they are free from parasitic capacitance effects, so they are used as a gas sensor is very easy. Highly reactive catalytic metals. So how to analyze the gas sensors? Because in the devices we have some metal gate products. You have highly reactive catalytic metals are used as gate electrode. When catalytic metals absorb the gas molecules, say carbon monoxide, then we have ammonia. These gases are acting as very toxic gases. So when catalytic metals absorb gas molecules, it changes their work function. Work function, the value of the energy required to make an electron from the to the valence band. This is the work function. DGNR based sensors can be utilized in various fields, medical, and monitoring, etc. So zigzag, what are the zigzag and armchair we are putting? So zigzag GNR is shown in the figure, and armchair GNR is based on half metallic and questionable band, but GNR is having similar property with wide and wet band gates. So GNR is double gate nano-based gas sensor. 2D material is used. Silicon is replaced by material. Analyzed metal used for electrode. It is used for the gas sensing application. Safety for environment, medical, and industrial monitoring process. 3 different gases, namely hydrogen and neon and oxygen, have been detected using the proposed gas sensor. For each gas, a distinct catalytic battery is used. So, because gases are the catalytic metals are sensing those gases. Each metal is sensing each gas. Silver and cobalt metals are used for detection of hydrogen, oxygen, and ammonia sensors respectively. Reaction between absorbed gas molecule and metal gate is this work function is the most important work function. Work is varying, then threshold voltage is varying. If threshold voltage is varying, then drain current is also varying, forming polarization. Such dipoles existence affects charge and the increase changes the voltage characteristic and voltage. So we observe the voltage and gases, we can realize the changes is done by the gases. It is to detect hydrogen, ammonia, and for hydrogen it is used, for ammonia silver is used, for cobalt and for oxygen cobalt is important metals are used for detection of hydrogen, oxygen, and ammonia gas. Figure structure is shown in the figure. So here silicon is used at the substrate, then source is grow over the source, channel is used, and then is there. And your gas molecules are reacting with metal side. The metal catalytic metals gas molecules are reacting, and the reaction work function is changed. Since function is changed, it is equivalently changing the threshold voltage. Threshold voltage will change the drain current, and drain current change will be measured as a sensitivity change of the particular device. Catalyst gases are what visible. Sensitivity is estimated based on the change in drain current threshold voltage. The effective modulation of the gate work function as the gas molecule's pressure is applied at the gate, and it is given by delta phi m is change in the metal gate work function depending on the partial gas pressure, and F indicates Faraday's constant, gas constant. The change in work function corresponds to the voltage. If there is a change in work function, our electrical parameter voltage also changes. The threshold voltage and drain current shifting the position due to the gas affects the advent voltage. So threshold voltage is a function of advent to function. And what are the results obtained? The table shows the sensitivity calculation for dual gate graphene nanoribbon vertical defect based sensor for different gases. So for oxygen, the changes of the work function is like 50 milli-electron volt, 100 milli-electron volt, and 150 milli-electron volt, and 200 milli-electron volt. And ammonia for hydrogen also, sensitivity for off current, on current, ion of, and VVIT, threshold voltage. For the different values of work function, the sensitivity for different gases are more. The sensitivity is highest. Sensitivity calculation sensitivity for is found to be highest for almost it is high for hydrogen. It is near about 1.084 for hydrogen gas. As gas concentration increases, the capital increasing and generate more carriers at the channel. The recombination rate is increasing, and this diminishes both the current. So make on current and off current rated off current due to the gas molecules, the device, the proposed graphene network DNR, graphene is a sensitive device. And show graphic changes. I know we have you can see it is with the change is plus increase of function. Del the in function of the metal catalytic gate. Metal with gas molecules. As a gas sensor. You see all kinds of and the reported proposed by our researchers and other reports. It has been found out that for this work, the sensitivity for reduces this 0.9% and for oxygen it is 0.1. It is the active sensor. The proposed device shows most sensitivity than other gas sensors. The DG, DNR, VT sensor offers a higher conformity than the others. It has two-dimensional area. Expected with the structure. So this is the DG, DNR, shows sensitivity structure and service for the gas molecules. Only those it was increment, it is 1%. And by the by oxygen up to 2% respectively. The maximum threshold voltage at work function 200 milliamp for various gases such as oxygen, 0.4 or 459 volts, 8 volts, and 0.8738 volt respectively. So you can see our sensitivity for the hydrogen is more, and maximum threshold voltage change obtained for hydrogen is higher. It is found 0.87 volts. Now the last stage of the presentation, and last few slides I have shown you the gas sensor application and the biosensor application. Now different application in RF energy means radio frequency energy harvesting. Radio frequency and harvesting systems have explored new perspectives in various scientific and clinical applications. In monitoring, biosensor RF rectifier with high sensitivity, high function efficiency. We want to devices. We use devices in case of RF rectifier because rectifier is high sensitivity, power consumption. Technology advancements high frequency bands. So the application is given the image so that low power applications and have high power conversion rates. So this is property can be met device. So that device can only be applicable for RF harvesting system. See, hello. And your energy harvesting and power management part related to switching rectifier, which converts to DC voltage booster, DC and voltage regulator. Our area of discussion is rectifier, which is converting RF signal to DC signal. So can you see changes of CMOS RF rectifier design? Many works study CMOS rectifier, connected charge key diode based CMOS rectifier designs and due to that process compatibility with CMOS circuit. These designs suffer from the efficiency loss used by large threshold voltage. Hence, maximum PC is relatively small. So in that case, the maximum PC is relatively small. And what are the key performance parameters of RF design? The key performance parameters are DC output power, DC output voltage, conversion efficiency. The performance parameters. So different model performance parameters are used, and power conversion efficiency defined as output by input. Output power, input by output power as loss. Loss, reverse conduction loss, switching loss, resistive loss. Various losses are also used to this. Capacitive switching loss, reverse is a reverse conduction loss. Redistribute is due to the charge redistribute with capacitors. Resistive is the loss due to the non-geometric changes. Design of rectifier. So now I have told you the design of rectifier. The circuit of the rectifier is shown in the figure. So equivalent rectifier RF rectifier design. This rectifier design. So equivalent rectifier is shown in the figure. From the signal is because voltage is to 200 people. Applied from the is 1 volt. Circuit is output is voltage. Reaction is charge. Instant power is power is the input. Small voltages of the device is the most important factor. When device which has small under voltage. This devices such as panel is an active device for application. So so here you can see two transistor topology. One is two transistors are used, M1 and M3 are used in this structure, and this is used as a rectifier. Two transistor topology. Output output and capacitor, load capacitance, and ground connection is shown. So what is the advantage? This is from conventional amplifier. MIN is on and M is off. And is more due to the soft bias and and next is four transistor topology. It is a four there are two devices and the M2 and 40 topology from the standard dynamic voltage cancellation. So in the M2 and M3 is the structure be an entry in our own and import of so T means here I will connect also register for entry topic. For first degrade is devices are used required topologies energy applications. The size by circular gate effect and circular gate P. And what are the forms? There are the figure. Input RF will show RF and the blue color is heterogeneous effect and red color showing for CG effect for circular effect. For the circular gate effect, the current is quite high as compared to the so rectifier of rectifier as compared to the so rectifier forms because voltage or CG effect is very low. So application of CG effect is much compared to the AA. So divided into 4 parts. Again, state divide substitution and divide now output so structure topology topology and topology. So what we have observed that output for the application is wider and so we can say that topology is with the parameter theta of HZ effect and is already I told you chunk effect. System of structures of we are showing as CG and micrometer that is millivolt per
Dear participants, I think Madam is disconnected because of heavy rains and internet connectivity is also down there. Maybe she is joining. Please just wait.
Hello.
Hello, ma'am. I think you're disconnected.
When are you disconnected?
Now,
Hello.
now you're audible, ma'am. You're audible. Please share your
okay.
screen and start it.
Up to which slide you have seen?
Yes, ma'am.
Hello.
Yes, ma'am.
Up to which slide? Which slide number you have seen?
91, 92, 92.
92. Okay.
Yes, ma'am.
Sometimes the net is or 92. Okay.
Madam, yeah, if you can stop the video of yours, then the bandwidth may be somewhat better.
Okay. 0.5.
Okay, let it be a trial.
You can off camera.
Yes,
You
ma'am.
can do camera side. So, various topics, rectifier topologies discussing where the defect can be used in rectifier and anti-application. The is 4 anti-topology where 4 resistor diode connect. To mitigate this, PTFET is replaced by diode connected anti-FET, and because it reduce voltage as an additional advantage. And defect. So current through the efficiency, low unknown voltage. And now okay, so I am now discussing. Can you see? Hello?
Yes, ma'am.
Yes, ma'am. Slide is visible. Slide is visible.
Okay. So then
Keep it in presentation mode, ma'am. Sorry.
Substitution, another is on state, off state, and another substitution region is shown. Now next we are discussing the output voltage. Output voltage, if you measure for the DC rectifier, it has been found better for 2P topology because vector is showing the 2P topology as compared to 4N and 4N. 4N means there are 4 types, but all are N-type defects. So we can conclude that here power conversion efficiency for 2 types of defects, different rectifiers are compared, and it has been found that if we use CD defect, it will give you better threshold swing because its value is less, 25 millivolt. Threshold voltage is also 0.5 volt. Power conversion efficiency is very high, 80%. And output voltage is 0.5 volt, which is better as compared to the heterojunction defect. Now I am concluding by remarks. High efficiency is obtained, high sensitivity is obtained for RF rectifier application. Reduced turn-on voltage and drive current can be improved, as well as unidirectional conduction can be obtained. High characteristics. The technological limitations of the conventional CMOS can be mitigated by replacing the CMOS devices with various defect structures. So, as energy harvesting applications, we have seen defect will provide you better characteristics. Now, this presentation I have considered the reference various papers, including most of them most of the researchers are done by myself and my PhD scholars. So this research, so I have RF energy harvesting. These researches are done by my students and these are published in very scientific transactions and based on the work contribution. So finally, I want to thank for hearing me and sorry for inconvenience caused due to the internet low internet connections in our area due to heavy rain.
Okay.
Hello.
Hello, ma'am. Thank you, ma'am.
Yeah. Okay. Thank you.
Thank you very much, ma'am.
Okay. Is there any question?
Madam, can I ask the participants if anyone having any doubts? Dear participants, if your side you are having any questions regarding the topic that have been delivered by Brinda ma'am. Otherwise, you may type in your chat box also. Madam is available for your any clarification. Madam, can you share?
Can ask.
Madam, can you share your PPTs, ma'am? So some of the participants are asking that we want to go through the slides.
You want to go through the slides from initially?
Some
Which
of
slide number?
No, slide number not, ma'am. They are asking the overall presentation.
They are asking.
Yes, ma'am.
Yes, I have to give you.
Okay, ma'am. You can send to me, then I will share to the participants.
Okay, okay. I will share you in your. Please send me email. I will share you via reply email to your inbox. Okay.
Okay.
Do you have any question regarding any doubt? Whatever I told.
Very good presentation.
Madam, one person asked a question. TFET fabrication, is it possible or not? That question a participant
TFET fabrication is possible. I have already fabricated because TFET fabrication process technology is compatible with the CMOS process technology. Since it is compatible, our IISc Bangalore is also performing some of the fabrications, and IIT Bombay has some. Purdue University also, they have also fabricated various TFET devices. And various, it is possible all the process technology are similar to that of CMOS, because already CMOS process technology is going on all the fabrication steps which we apply to TFET, that is also similar. That is why we can fabricate. But the problem is that TFET devices parameters need to be used. Some of the parameters used some of the that is why research is still going on.
Okay, ma'am.
Hello.
Ma'am, one more question is asked by another participant. Is there any open source tool that is available to simulate TFET circuits?
No open source tool is available. No open source tool is available. Stick software to this device because it is a new structure. You cannot design structure. you have to use the proper physics models. Then only this type of software are not open source software. And that is why, since these are not open source software, people can use AI-based tools. Because AI-based tools nowadays, you can use fuzzy logic and genetic algorithms. This can also be used to design the defect parameters. Then what we can do, the parameters can verify existing literature papers. You could use AI-based orientation, objective functions developed, and you can give some of the electrical parameters as the constraints. At central voltage, you are optimizing with the parameter of drain current, electric field. Then you can optimize using some tools, and you can find the results which are given in literature either from experiment or from ticket simulation, which are already published. You have understood my reply?
Yes, ma'am. Okay. If any participant is ready with any questions.
Okay, if you okay, I can share my PPT after the presentation. Okay.
Okay, ma'am. Definitely.
Okay. So can I leave?
Yes, ma'am. Ma'am, thank you very much for accepting our invitation and giving a good presentation on the latest VLSI technology with the AI approach. Thank you very much, ma'am.
Yes. Okay. Thank you, everyone.
Thank you, ma'am.
Okay.
Thank you, madam. Thank you very much. Yeah.
Okay.
Thank you.
Thank you.
Sir, I think recording end sir.
Okay, sir.
Recording end చేసి end